Welcome to the Week 9 guided practice for Chapter 10, Unsupervised Learning Clustering Using K-means. In this walkthrough, we will complete the student practice from beginning to end. The page you see is the same unanswered version provided to students. The blank underscores and todo comments identify the areas that must be completed. I will type each solution directly into the appropriate code section, explain what the code does, review the output, and then scroll to the next part. The goal is not only to obtain the correct result, the goal is to understand the complete K-means workflow and why each step is necessary. This activity has two main stages. First, we use synthetic data to understand the mechanics of K-means, including scaling, cluster assignment, centroids, and silhouette analysis. Second, we apply the same workflow to a Bermuda short sizing case study. By the end, you should be able to prepare numerical data, train K-means, inspect cluster centers, compare silhouette scores, and interpret the clusters without assuming that the numerical labels have built-in meaning. Every cell marked todo must be completed. The completed notebook should also run from top to bottom withoot errors. We begin by importing the required libraries. NumPy supports numerical arrays and calculations. Pandas provides data frames for working with tabular data. Matplotlib creates the scatter plots and line charts used throughout the exercise. From scikit-learn, make blobs generate synthetic clustering data. Standard scalar standardizes numerical features. K-means performs clustering, and silhouette score evaluates cluster cohesion and separation. Run this cell before continuing. The confirmation message tells us that the imports completed successfully. In part 2, we generate an unlabeled dataset with make blobs set n samples to 300, which creates 300 observations, set centers to 3, so the data generator creates 3 underlying groups. A cluster standard deviation of 1.0 controls the spread of the generated points. The random state of 42 makes the result reproducible. We store the numerical feature matrix in capital X. The underscore receives the generated labels, but we intentionally ignore them. K-means is an unsupervised algorithm, so we will train it using only X. The output confirms that X contains 300 rows and 2 feature columns. K-means is based on distance, so feature scale matters. We create a standard scalar and use fit transform on X. The fit step learns the mean and standard deviation of each feature. The transform step uses those values to standardize the observations. After scaling, each feature should have a mean close to 0 and a standard deviation close to 1. Small floating point values near 0 are normal. Standardization prevents one feature from dominating distance merely because it uses larger numerical units. Next, we visualize the two feature columns. X column, 0 selects every row from the first feature. X column, 1 selects every row from the second feature. Notice that all observations initially use the same visual style. We do not color the points by their generated classes because those labels are not available to the clustering model. The purpose of K-means is to examine this numerical structure and create its own cluster assignments. We now create the K-means model. Set n clusters to 3 because our first model will look for 3 groups. K-means++ provides a more deliberate initialization of the centroids. The random state makes the result reproducible. The n-init setting uses the current scikit-learn initialization behavior. Next, call fitPredict with the scale data. This trains the model and returns one cluster label for every observation. In this generated example, each cluster contains 100 observations. Remember that labels 0, 1, and 2 are arbitrary identifiers. They do not represent an order or level of quality. The fitted model exposes several useful properties. Cluster center returns the centroid coordinates in the scaled feature space. Inertia is the sum of square distances from each observation to its assigned centroid. A lower inertia means the points are more compact around their centers for the selected K and iter. Report how many iterations were required for the model to converge. In this run, the model converges quickly. The centroid coordinates are standardized values, not original measurement units. We can now visualize the assignment. The two scaled feature columns define the scatter plot coordinates. The C argument receives cluster labels 3, which applies one color to each cluster. The second scatter call adds the centroid locations using a large X marker. This visualization confirms that the algorithm found 3 compact groups. The colors help us inspect the result, but they do not create meaningful names. The numerical cluster identifiers remain arbitrary. Part 5 evaluates possible values of K with the silhouette coefficient. For each observation, the value A represents the average distance to points in its own cluster. The value B represents the lowest average distance to a neighboring cluster. The general formula is B minus A divided by the larger of A and B. A higher average silhouette score usually indicates that observations are compact within their clusters and well separated from neighboring clusters. We will calculate the score for several possible values of k. Create an empty dictionary named silhouette scores. The range begins at 2 because silhouette analysis requires at least 2 clusters. The ending value is 9 because Python excludes the upper endpoint, giving us k values from 2 through 8. For each candidate k, create a new k-means model. Fit the model to escalate and obtain its labels. Then calculate the silhouette score using the same scaled feature matrix and the assigned labels. Store the score using k as the dictionary key. The resulting table lets us compare the candidates directly. To identify the strongest candidate, use max on the silhouette score dictionary. The key argument should be silhouette scores.get. This tells Python to select the dictionary key associated with the largest score rather than selecting the largest k value. The result is k equal to 3 with an average silhouette score of approximately 0.8482. This matches the 3 centers used to generate the synthetic dataset. For the chart, place the dictionary keys on the horizontal axis and the score values on the vertical axis. The line reaches its highest point at k equal to 3. In the reflection, explain that k equals 3 produced the strongest silhouette score and that it matches the synthetic dataset's 3 generated centers. Also, explain why silhouette should be treated as evidence rather than an automatic decision. It measures geometric cohesion and separation, but it does not understand whether the clusters are meaningful, fair, stable, or useful for a real application. The second half of the guided practice applies k-means to a practical sizing scenario. The dataset contains waist circumference and upper leg length. It does not contain predefined size labels. Our goal is to inspect and clean the measurements, compare possible values of k, and then explore 4 proposed product sizes. The measurements are embedded directly in the notebook, so students do not need to download an external file. Notice that the dataset intentionally contains missing values. We will identify and remove those incomplete rows before clustering. We begin by inspecting the data frame. The shape shows 40 rows and 2 columns. Head displays the first 5 observations is null. Sum counts the missing values in each column. There is 1 missing waist value and 1 missing upper leg length value. Describe provides summary statistics such as the count, mean, standard deviation, minimum, quartiles, and maximum. Inspection should always occur before cleaning or modeling. For this guided activity, we remove rows containing missing measurements with dropna. We first select the 2 relevant columns and then call the method. The original dataset contains 40 rows. After removing the 2 incomplete observations, 38 rows remain. In a real project, dropping missing data should be justified carefully because missingness can introduce bias or remove important portions of the population. The clean measurements are plotted with waist circumference on the horizontal axis and upper leg length on the vertical axis. Before clustering, all observations use the same visual style. The plot shows a strong relationship between the 2 measurements. However, no predefined product sizes exist yet. K-means will organize the measurements according to distance in the selected feature space. Create a new standard scalar specifically for the shorts dataset. Use fit_transform on clean shirts. The new scalar learns the means and standard deviations of waist and upper leg length. The output contains 38 rows and 2 scale features. We keep this fitted scalar because it will later convert the centroid coordinates back into centimeters and transform new customer measurements consistently. Now repeat the silhouette comparison using the scale shorts measurements. The range begins at 2 and ends before 7, producing k values from 2 through 6. For each candidate, fit a new k-means model to shorts case. Calculate the silhouette score using the scale data and that model's labels. The scores gradually decrease as k increases. For this dataset, k equal to 2 provides the strongest average silhouette score. Use the same dictionary technique to identify the largest score. The strongest silhouette candidate is k equal to 2 with a score of approximately 0.5874. The chart provides a visual comparison and confirms the same result. This does not mean the company is required to manufacture only 2 sizes. It means 2 clusters provide the strongest geometric separation among the tested candidates under this metric. Part 10 introduces an important distinction. The silhouette score suggests that 2 groups provide the strongest separation. The company, however, wants to explore 4 proposed sizes. Choosing 4 clusters represents an operational decision that balances customer coverage, inventory, manufacturing complexity, and product strategy. The mathematical score remains useful evidence, but it does not make the complete business decision. This trade-off should be documented rather than hidden. Create a new k-means model with 4 clusters. The initialization and reproducibility settings remain the same. Call fitPredict using the scale shorts data. The return labels divide the 38 observations among 4 groups. The raw cluster counts show the number of observations assigned to each identifier. Again, cluster 0 through cluster 3 are arbitrary labels. They are not yet order size names. The fitted model stores its centroids in cluster centers. Because the model was trained on standardized data, the raw centers are also expressed in standardized units. To interpret them as measurements, use the fitted shorts scalar and call inverse transformat. The converted values are now expressed in the original waist and upper leg length units. Only after this conversion is it appropriate to discuss the centers as possible product measurement. The raw cluster identifiers are arbitrary, so we sort the centroid table by waist circumference. After sorting, reset the index and assign the provisional names, size 1 through size 4. The resulting centers are approximately 68.23 and 36.08 for size 1. Size 2 is approximately 77.56 and 38.82. Size 3 is approximately 88.21 and 41.75. Size 4 is approximately 100.31 and 45.13. These values are representative centroids, not validated manufacturing specifications. The final visualization uses the clean original measurements as the point coordinates. The C argument receives the 4 cluster labels. The centroid markers use the inverse transform values, so they appear in the same original measurement units as the observations. This chart helps us inspect the proposed groups and their representative centers. The visual results should still be evaluated with fit testing, additional measurements, and broader customer data before any manufacturing decision. The new observation contains a waist measurement of 80 centimeters and an upper leg length of 42 centimeters. It must first be transformed using the fitted short scalar. Do not call fit transform on the new row because that would learn a new scale from one observation. After transformation, call the fitted k-means models predict method. The result is raw cluster 3 for this run. To translate that number into a proposed size name, we need the documented mapping between raw cluster identifiers and the sorted centroid table. The raw number alone does not automatically mean size 3. The final reflection verifies conceptual understanding. K-means is unsupervised because the model receives features without known target labels. We standardize because k-means uses distance and large numerical ranges can dominate the calculation. Cluster numbers are arbitrary identifiers rather than ordered categories. A high silhouette score suggests compact clusters with stronger separation from neighboring groups. A company may choose 4 product sizes even when another K has a higher score because operational needs and customer coverage also matter. Before using centroids as manufacturing specifications, the company should consider population representation, missing data bias, additional body measurements, accessibility, fit testing, and production tolerances. Before submitting the guided practice, confirm that every todo cell has been completed. Run the notebook from the first cell to the final cell and verify that no errors occur. Make sure all charts are visible. Confirm that the silhouette score tables are displayed and that the 4 centroids appear in their original measurement units. Answer both reflection sections in complete sentences. Finally, save the completed notebook with your name included in the file name as PDF. This concludes the Week 9 guided practice solution walkthrough for k-means clustering.